All right, let's talk about a high-stakes battle that's happening right now, on a scale so small you can't even see it. It's this constant fight against heat, friction, and total failure that's going on inside the machines that build, well, pretty much everything in our modern world. And the stakes? They couldn't be higher. So, let me ask you something. I want you to picture a jet engine turbine blade, spinning at incredible speeds. Then think about a life-saving surgical implant, and maybe the metal case of the phone that's in your pocket. What on earth could possibly connect these completely different things? Well, the answer is kinda wild. Every single one of them was carved into its final shape by a cutting tool. A tiny, super hard piece of metal that's under enormous pressure and is constantly, and I mean constantly, on the verge of breaking down. And it's right there, on that fragile edge, where our whole story begins.
You see, this constant threat of just shattering, it leads us to one of the most important ideas in all of manufacturing. The idea that every single tool has its own ticking clock.
And that clock is what we call tool life. Now, the definition sounds simple, right? It's just how long a tool can cut effectively before it wears out. But the problem it represents, it's incredibly complex. Because if you get this wrong, your entire production line can just grind to a halt.
And we're not just talking about a tool getting a little dull here. No way. As the research makes really clear, a worn-out tool needs more force, it sucks up more energy, and the quality of the thing it's making gets worse and worse. So what does that mean? It means higher costs, more waste, and frankly, lower quality parts. It's a big deal.
Now, this battle gets particularly intense, absolutely brutal, when you're trying to machine what engineers call hard-to-cut materials. We're talking about the super strong stuff used in aerospace and medicine, like titanium alloys and Inconel. These materials, they fight back. They generate so much heat and pressure that they can just obliterate cutting tools with terrifying speed.
So if a tool's life is a constant battle, who are the enemies? Let's take a look at the villains, the things responsible for a tool's demise. Turns out it's a whole gang of microscopic attackers.
This here shows the two main forms of attack. Over on the left, you've got flank wear. Just imagine the side of the tool being slowly but surely sanded down by friction. It's gradual, but it's usually the #1 sign that the tool's life is about over. But then on the right, you have something way more dramatic, crater wear. This is literally a pit, a crater, that gets carved into the top of the tool by scorching hot metal chips flowing over it like lava. If that thing gets too deep, the whole cutting edge can just snap. Catastrophic failure.
But it's not just friction. This whole gang of culprits, they all work together. You've got adhesion, which is when bits of the material being cut literally weld themselves onto the tool. Then there's diffusion, which is even sneakier. Atoms actually jump from the workpiece to the tool, weakening it from the inside out. All of these things team up to destroy that perfectly sharp edge.
Okay, so it might sound like a losing battle, right? But here's the cool part. Engineers have come up with an incredible arsenal of tricks and technologies to fight back and stretch out a tool's life. Let's look at their weapons.
The very first line of defense is kind of like giving the tool a suit of high-tech body armor. We're talking about incredibly thin, yet unbelievably hard, advanced coatings.
And this chart, wow, it just brilliantly shows the difference they make. Take a look at the bar on the far left. That's our plain, uncoated tool, the baseline. Now, just by adding a standard coating, something like titanium aluminum nitride or TALN, you can see its life jumps by 150%. Then you move over to the really advanced nanocomposite coatings, and boom, the tool's life shoots up by over 250%. It's amazing. These coatings work by being super hard and slick, but they also form this self-protecting oxide layer at high temps, basically creating a ceramic shield right where it's hottest.
And the precision here, it is just astounding. Research shows the absolute sweet spot for these coatings is between 6.5 and 8 micrometers thick. For perspective, a human hair is about 70. So if you go too thin, it just wears away. Too thick, and it gets brittle and cracks. It is a microscopic balancing act.
All right, so the next weapon in the arsenal is all about winning the thermal war. Cutting metal generates a massive amount of heat right at the tip of that tool, so controlling that temperature is absolutely critical.
One of the cleverest strategies is called minimum quantity lubrication, or MQL for short. So instead of just flooding the machine with coolant, MQL is way smarter. You mix just a tiny drop of oil with compressed air, and that creates this really fine mist. This mist is then aimed with pinpoint accuracy right at the cutting zone, giving you just enough cooling and lubrication to protect the tool. It's way more efficient and a lot better for the environment.
But the most modern line of defense, The cutting-edge stuff, it isn't physical at all. It's digital. We're talking about embedding sensors right into the machines to listen to vibrations, to monitor temperature, and then using artificial intelligence to predict wear before it becomes a problem.
So all of this technology, it's pushing this microscopic battle against wear and tear into a completely new era.
You see, the entire battlefield is shifting right under our feet. The fight is moving away from just relying on stronger materials and better armor,
And it's heading towards something way more dynamic, much more intelligent. And this is the new frontier that researchers are exploring right now. Using real-time data from acoustic and thermal sensors to feed AI models. These models can literally hear, feel, and see the signs of wear long before any human ever could, predicting a failure with enough time to actually prevent it.
And that leaves us with this really fascinating kind of mind-bending final thought. As we go from just reacting to tool failure to actually predicting it, are we on the verge of a world where our tools are so smart they can avoid wear altogether? I mean, could we actually be approaching the end of wear itself? Something to think about.